Welcome to the exercise about the toxic spherical particles. These particles are assumed to be perfectly spherical and they will evaporate when released into the air. So we start off with the mass balance for this situation. This is the derivative of the mass with respect to time equals minus the area times the mass flux. The mass on the left-hand side of the equality sign can be replaced by the density times the volume. And on the other side of the equality sign, the expression for the area is pi times the square of the diameter, so that of a sphere. And the mass flux equals k times the difference between the concentration at the surface of the particle, which can be derived from the ideal gas law, and the concentration at infinite distance from the particle, and this is 0. The expression for k is the Sherwood number times the diffusion coefficient divided by the particle diameter. So first of all, we assume that the only type of mass transport at play is diffusion. In this case, the Sherwood number is 2 since the particle is spherical. Now we copy the expression that we first used for the mass flux and we fill in all the numbers as given in the beginning of the exercise. And we find that the mass flux is 4.01 times 10 to the power of minus 7 kilograms per meter squared per second. So we can see that mass transfer occurs at a very slow rate. In 2.3.3, we are asked to calculate the time needed for the diameter of the particle to be halved. We can calculate this by integrating the mass balance. We started from the expression we found earlier, and then we derive the expression for the volume of a sphere in order to obtain the derivative of the diameter with respect to time. So we replace the volume by pi over 6 times the diameter to the power of 3. And as we know, when just deriving this becomes 3d squared. And now integrating this and isolating t, we can calculate the time needed. So as we can see, if we integrate the left side of the equality sign, this gives half of d squared. And to the right, we will just get t. Remember, the border conditions we chose are that at the beginning, so at the moment t is 0, the diameter is d0. And at the moment t, which we are looking for, the diameter is half of that at the beginning. So integrating this and isolating t will give 62.23 days. So as you can see, 62 days, that's a very long time. However, we have made some assumptions that could cause for this value to be wrong. Since the situation described takes place outside, we cannot assume that the medium is not moving, as is the case with diffusion. We have to take into account convection. We thus assume that there's wind outside with an average velocity of 5 meters per second. In this case, we have a new expression for the Sherwood number. In order to determine this expression, we need to know in which range the values of Reynolds number and Schmidt's number lie. This is why we calculate the value of these numbers at the moment t is 0, and we find that Reynolds number lies between 10 and 10,000. And Schmidt is larger than 0.7. We can thus use the expression for the Sherwood number 2 plus 0.66 times the Reynolds number to the power of a half and Schmidt's number to the power of a third. So now we will calculate the new Sherwood's number. If we fill in the found values, we find that Sherwood's number is 55.655. Next, if we calculate the mass flux with this new value for the Sherwood number, we find 0.116 times 10 to the power of minus 5, which is almost 30 times larger than with diffusion. For the last question, so 3.2.7, we are asked again to calculate the time needed for the diameter of the particle to be halved. However, with this new Sherwood expression, integration will become very complicated. This is why we are giving a new simplified expression that will give us a realistic result. So now the Sherwood number will be 0.66 times the Reynolds number divided by density of air to the power of half times Schmidt's number to the power of a third. And this gives us a new differential equation. So 1.32 is 2 times 0.66. And we write out each variable separately with their own power. In the end, we integrate this and we finally isolate T. This gives 0.91 days. As you can see, the particle evaporated much faster when convection is taken into account than when we only look at diffusion. Thank you for watching the video and good luck with the rest of the exercises.